It's a great pleasure to introduce David Kotz. I've known David Kotz for many, many years, probably 10 years or so now. When I first met him, I was introduced to David as one of the leaders in the mobile systems community, Mobisys and so on. And since then, I've come to know David as a leader in a number of other areas as well. So at the intersection of mobile systems and security, I think of David as one of the thought leaders, and also issues related to healthcare, mobile technologies, and mobile security. It's a great pleasure to have David here today. Oh, by the way, I should also mention that, David, you're a member of the U.S. Healthcare IT Policy Committee. So this recognition of David as being one of the thought leaders is not just my own perspective, but that of the U.S. government as well, and so on. So it is really a great pleasure to have David here today, and as one of the leaders in the mobile systems community, to hear his thoughts on one of those topics, energy-efficient, multi-application wearable platform.
Great, thanks, Yoshi. I really appreciate it. It's great to be here. I always enjoy visiting UW. It's probably been 5 or 6 years or something like that since I was here last. And it's my pleasure to share with you some of the work that we're doing in mobile health and the cross between mobile health and security and privacy at Dartmouth. And in this particular project, in collaboration with my colleagues at Clemson University in South Carolina. As you can imagine, any system building project involves a lot of people, and so these are some of the people that are currently involved in the Amulet project, and there's quite a few more, and I'll name them all toward the end. I'm happy to answer questions, so at any time, please get my attention. Some of you are way up there in the back, so it might be difficult. You may have to, make a lot of noise, but I'm happy to answer questions anytime. So one of the things that I find when working in a buzzword-laden field like mHealth is that you need to define your buzzwords. So mHealth is one of those that has been used so heavily that it sort of has lost its meaning. Here's what I mean when I talk about mHealth. So it's the application of mobile computing and communications technology to either the delivery of healthcare or the collection of health information. And even that's a pretty broad definition, including the use of mobile tech in the clinical setting by clinical staff, for example, using tablets and phones as they go about doing their work in the clinic. Or for that matter, put the mobile technology on the patients in the clinical setting to monitor the patients or to help manage their drug dosage and so forth. All of these are mobile devices and mobile health in the clinical setting. Or you could send the patient home with some technology to monitor her condition. Maybe it's a chronic disease like heart disease or diabetes, or maybe it's post-surgical care, or maybe it's an elderly person who needs some Alzheimer's support, et cetera. So technology often goes outside the clinical setting, but still clinical applications. Or you might sort of broaden it even further, as is certainly the case in the consumer market, to wellness. So not just health care in a formal sense, but health and wellness. So using technology to support an individual's interest in staying fit, stopping smoking, losing weight, what have you. And of course, another category of mHealth is in the developing world, using this technology to help scale healthcare systems to support millions and billions of people, rural areas, and so forth. So all of these fall under the mHealth umbrella. And the nice thing is that the technology is evolving extremely rapidly with a lot of interesting opportunities. Smartphones, of course, is one type of mobile technology that's very powerful. They include lots of sensors in them, mostly there for other purposes, but various clever people, including some here, have retasked those sensors to do health-related measurements or monitoring. Everything from physiological monitoring to emotional or behavioral monitoring. Now, of course, it's not just phones. There are lots of devices that you can carry or wear that will help measure or monitor or manage your health. Some of them, most of them, all of them in this picture focus specifically on health-related applications. These are all wearables. So there's another buzz phrase. I don't like it when people say wearables and they mean a wristband. But wearables could be worn in many places. And then there are other devices that you may not wear all the time, or you may never wear, like a bathroom scale. You step on it. And in some of them, you never actually physically contact, like an environmental sensor. Some of them are personal. Some of them are shared. All the people in your household might use the bathroom scale. And some of them are broadcasting their information, like these environmental monitors. All of these devices fall, in my mind, under the mHealth category. So I'm interested in the security and privacy issues that come up when you're dealing with mHealth applications. And so some people ask me, well, what's so different about mobile health relative to other healthcare security and privacy issues. And these are some of the ones that I see when comparing to healthcare IT or comparing to mobile IT. So the security issues come up especially in situations where the technology is directly impacting your health, like an insulin pump. Obviously, if someone manages to hack that device or that application, they can have immediate and very personal impact on your physical well-being, and so that's a major issue. Hacking my bank account is unfortunate and frustrating and troublesome, but it's not nearly as personal and immediate as killing me. Privacy is, of course, a big issue here because we're collecting data that's very personal. It's about me, literally about me and my body and my behavior and my physiology, and so that's very sensitive. Relative to, say, clinical health data, I go to the hospital once a year. I get a checkup. They collect, 20 parameters from me, height, weight, blood pressure, and that kind of stuff. They put it in their computer system. There's a ton more data in mHealth because some of these applications are collecting data every day or every hour or even every millisecond. And so there's a lot more data. And that data is often more diverse. They're collecting not just physiological information, but lifestyle and personal social activity, contextual information that is relevant to health applications, but also can tell you a lot more about me. And the uses of the data, the applications that people have in mind for mobile health technology are more diverse than just simply clinically diagnosing and treating disease. They might be helping you reduce stress and be more organized and be more mentally happy or something like that, a much broader range of applications. So mHealth is different in those regards. So what I want to talk about mostly today is this project we call Amulet. And the goal here was to design a kind of a personal hub for collecting all this mobile health data, running applications to process and make use of that data and interact with the person. And the obvious platform for doing that is the smartphone. Smartphones are programmable. You can load apps on them. They're kind of pervasive. Almost everybody has one, at least in this country. And so that seems like a logical place to do this work. But as we all know, smartphones are not invulnerable. They can be stolen or they can be broken. My teenagers' phones often look like this. Or you might just leave them behind. I do that often. In fact, when I'm giving a talk, I often leave my phone somewhere else. I put it here. It's not on my body. It's not measuring me right now. It's not in contact with me. So it has less of an ability to measure what it might need to measure. Also, if it were to pop up a notification or ask me a question, I'm not necessarily there. And in fact, anyone with small kids might know that when you loan your phone to them to play a game or something in the back of the car, if a notification pops up and it has an OK button, they click OK, right? So it says, increase daddy's insulin dose, OK. It's not necessarily me that's using that phone. So the Amulet is designed to be a wearable device that's physically attached to me. And we like this name because it evokes this notion of safety and security and protection. And so what we're looking for then is a wrist-mounted mHealth platform that's with the user at all times because it's literally strapped to you. And it can authenticate its wearer. We have a related project in which we have biometrically recognized the person who puts on the bracelet. And it can be independent of the computer. It's physically separate from my laptop or my smartphone, on which I'm doing email and browsing and playing games and doing all this other stuff that basically loads those platforms with malware. And this is separate and running only health-related apps. And it's a trustworthy interface to me because it knows that it's on me. It can present those notifications and questions to me and be more discreet, know that it's talking to me instead of to whoever picks up my phone. And it has a network. It can manage a body area network of other devices like some of those that I showed you. I don't believe you can do everything in a phone. I don't believe you can do everything in a wrist wearable. Some things need to be measured at the chest, like the heart. Some things need to be measured, on your face or on your ankles or what have you, depending on what you're trying to measure. Post-knee surgery patients may need devices like a knee brace that's measuring their knee behavior, that kind of stuff. So there are wrist wearables out there. Actually, when we proposed Amulet at Hot Mobile 2012, I remember at least one very prominent member of the community standing up and saying, nobody wears wristwatches anymore. This is crazy. Why are you bothering? Now, of course, we now see the market is full of wristbands and wristwatches, smartwatches, and these are kind of two endpoints of the market right now. They're blurring. Those lines are blurring as the wristbands become more capable and the smartwatches start taking on fitness activity tracking. They have pros and cons, though. The wristbands are designed for and generally have a very long battery life on the order of weeks, which is great. But they tend to be very closed. They don't run other apps. They don't have the flexibility to be reprogrammed in any way. The smartwatches have more flexibility. Maybe you can install apps, but they tend to be very short-lived, maybe 1 day of battery life. And what we want is a long battery life platform that allows us to install multiple apps from multiple developers and has strong privacy and security guarantees. So none of the current platforms really provide those things. So we set out to build Amulet. And this is what we call sort of more generally computational jewelry. It's something you would wear, and if we were actually industrial design people, you might actually like the looks of it. In a bracelet form, runs multiple applications with long battery life and strong security. This is an Amulet. Actually, this is the slightly previous version of the Amulet from October, and I'll show you a lot more details. So the Amulet platform is really a collection of things. It's the hardware, a custom wearable, plus it's the software, custom operating system, custom compiler, custom applications, custom development tools, all of which together help us to achieve the goals. So here's the big picture. You see in the lower left is a patient or a person who's wearing an amulet and who has some health goals that they're trying to achieve. He is wearing some other devices on the wrist, on the ankle, on the waist, and so forth. And all of those are part of the amulet's body area network. And when available, the companion smartphone can be used as a gateway from the amulet to the cloud. And the Amulet Cloud serves a couple of purposes. One is it's a repository for the data where it could then be shared to the clinician or caregiver or family member, what have you. And the other is that it's a source for applications. So their developers register their applications with the Amulet Cloud. The patient or person can then say, I want this, this, and this application. Maybe some of them are recommended by my doctor. And the Amulet Cloud produces a custom firmware image for me, downloads it to my Amulet. And that's sort of the overall picture. We have not built the cloud part of this yet, but you get the idea, I hope. So in the rest of the talk, I'm going to talk about the design of the Amulet and its implementation and its evaluation. So when we set out to design it, we had several goals in mind. Mostly, we wanted to be able to support multiple applications. If the goal is a single application wristband, there are ways to do that. There are lots of products like that out there. But many people have multiple health goals, multiple health needs, and they might want a fitness application and a stress relieving application and a smoking cessation application and a diabetes management application. And they don't want to wear 4 different wristbands. There's strong security. This has been designed in from the start, and I'll show you how we do that. We want to obviously protect applications from each other. They're written by different developers, so there's no one team that can agree, okay, here's how we're going to play nice in this platform. And we want long battery lifetime. So typically that's on a smartwatch now hours and days. We want to measure hours in weeks and months. And in order to make it easier for app developers to build these apps, we want to build tools for them, in particular tools that help them manage energy so we can get this long battery life. And of course, we want the platform to be usable, not just for the ultimate wearer, but also for the developer and the researcher. And by the researcher, I mean perhaps an mHealth researcher who wants to use the Amulet in his or her research program, putting it on subjects, volunteers, to collect data. And we want it to be open. In fact, we've released it now 2 weeks ago on GitHub. You can download the hardware, software, fab your own Amulet, and go have fun. So here's what the device looks like today. Well, the case is slightly upgraded since that one, but here's what's inside it. So there's several sensors, a gyroscope and an accelerometer, and a light sensor, a UV light sensor, a temperature sensor, a sound sensor, and a battery level sensor. We have 2 microcontrollers in there. It's an ARM Cortex M0. That's basically a Bluetooth chip, a BLE chip. and then an MSP430, which is where we run our apps. It's a very low power, fairly limited capability microcontroller. You can see it only has 2K of RAM, of SRAM, and 128K of FRAM, which is persistent, non-volatile memory. And a micro SD card slot, which means we can store removable, I think our limit is either 2 gig or 8 gig cards that can store logging data from the apps. It has a BLE radio, which it uses to communicate either in central or peripheral mode, which means it can talk to other body area sensors, which are peripherals, or it can be a peripheral and talk to a smartphone. It has a small display. This is a sort of an e-ink type display, meaning that you can charge. It costs you almost nothing in energy to just have the display on. But if you change a pixel, that costs more energy. So for just a quick glanceable display that shows some current status information, it costs us almost nothing. A couple of LEDs, a haptic vibrator, which means like your smartphone's silent mode, it buzzes, has that inside. 2 buttons and a slider. So when we want to do sort of pick list, pick from a menu type thing, you can slide up and down. And you could use the accelerometer for gesture input, although we haven't done that ourselves, and a battery. So we have some apps that we've been developing, mostly proof of concept applications. There's actually a video running here of a heart rate monitoring app, just a simple Bluetooth connection to an external commercial heart rate monitor that then sends back the heart rate, and this app displays it and or logs it. But our main apps that we're focused on right now are really twofold. One is on stress monitoring. We're working with behavioral health researchers who mostly focus on addictive behavior, and they believe that a lot of addictive behavior is driven by stress. So people then relieve their stress through smoking, drinking, drugs, etc. And they want to understand how the connection between stress and behavior, and also eventually intervene in helping people prevent the unhealthy behavior. So they want a stress measurement tool. And so our Amulet plus a GSR sensor and an ECG sensor is our goal, is our platform for measuring stress. Another one is an activity monitoring app that measures, that we're using with a doctor of geriatrics who studies or treats obese elderly patients. And his goal is to help them retain function so they can live at home longer. And that he gives them exercises to do at home, not to lose weight, but just to retain strength and mobility. And so he has several different apps that he needs and we're developing to support his research. So what does an app look like? So an app is written, well, it's written in C ultimately, but it starts actually with the programmer drawing out a state machine using a graphical interface. This is not ours, it's a tool called QP. They draw the set of states that the app might be in and the set of transitions between states. So if you think of most of these apps, they're idle, they're waiting for new sensor data. When new sensor data comes in, they do something. They process that data, they make a decision, they update the display, log something to the SD card, whatever, and then go back to being idle. So the programmer figures out, okay, I'm in this state, and then when I get this sensor data, I go to this state, and I come back to that state. And then they just have to write C code snippets to handle the events. So they write a set of event handlers in C. And then this API allows the Amulet OS API allows apps to get access to certain things, like to subscribe to sensor data. I want to receive accelerometer readings, or I want to receive updates of the battery or level, or every time they press the button, send me an event, that kind of thing. And the Amulet OS has these core services for logging to the SD card or setting timers to get events when a timer goes off, and so forth. So how do we build these applications, and really how do we build the firmware image that goes into the Amulet? So the image is actually a combination of multiple apps. So the end user selects the set of apps that they want, and the firmware compiler toolchain collects those apps, compiles them all together, and produces a firmware image for you. This toolchain has several important roles. It has to make sure that these apps are isolated from each other, and of course profile them, generate enough information so that we can predict the energy consumption. So let me show you what this looks like. It's actually a sequence of little tools that work together, and I'll step through them. So the first step is to analyze the application to make sure that it is behaving properly. And that means that it can only call certain API functions, Amulet operating system functions. And we have a configuration file in which you can say, the heart rate application is allowed to call the heart rate APIs, and the stress measurement application is allowed to call the heart rate and the GSR APIs, and that kind of thing. And so we basically do access control on a function-by-function basis. And then we also restrict C. So the C language is very powerful and very challenging, as you know, with lots of pointers. People could generate a pointer and access any piece of memory. To prevent that, we ban the use of pointers and dynamic memory allocation. And to keep the stack size small and predictable, we don't allow recursion. And so this means that programmers have to work in a little bit different language or have to port their app to a little bit different structure than they might be used to, but it allows our tools to make strong guarantees about the end result. So then after the application has been checked and translated a little bit, for example, to convert the in a function call with an array, you can actually pass an array by reference, which you can't do in C, but we make it possible in Amulet C. Then we pass it through a resource profiler that's going to measure how this application uses various resources, memory, instructions, API calls, and I'll talk more about that. And then we merge them all together into one firmware image with the compiler and linker. Notice this lower right, the resource profile also goes to ArtView. That's our graphical view of the resource consumption, and I'll show you that in a moment. That's really the thing I want to focus on right now is this resource profiling. And the reason is that we wanted long battery life, and so we need to design the system for low power, but we also need to make sure that the applications are designed for low power operation or for long battery life. And that's harder for developers to do, and so we want to give them tools to make that possible. So the Amulet Resource Profiler helps application developers to do that, and it does two things really. First, it models the Amulet itself. So we actually measure sort of micro benchmarks to characterize all the energy cost of all the different pieces of the Amulet and all the different functions that you might call. And then we model each application at compile time. Every time you compile the app, in fact, is remodeling that application to count instructions and so forth. So the first step is to profile the device. And so we actually have a custom chassis, a hardware chassis that we snap onto the Amulet board that drives the Amulet through a sequence of predefined sort of micro benchmarks to measure how much does this API cost in energy and in time, and how much does every instruction cost, how much does it cost to write to the SD card, and so forth. It just generates all this information, and you save it. So you do this once for each model of the Amulet. And then for each app, the compiler or the application profiler counts instructions, counts every API call, counts all the different things that the application might do and constructs the model of the energy consumption and memory consumption of this app. And so then this graphical interface called ArtView consumes these profiles and provides the user, the developer, with an interactive model of the overall device lifetime. So for a given mix of apps, the programmer can say, I'm writing application A, but I'm going to suppose that the user chooses applications B, D, and X. And what if I mix those together in my firmware? How would the battery lifetime run on that Amulet? And so they can tweak those parameters. Let's see how that looks. Here's the view. It's a little hard to see here, but I'm going to show you a live version in a moment. But just for orientation, in the upper left is the state machine. So the compiler knows the state machine because you've laid it out for the tools, and it's showing each state that this application might be and the transitions between state, and it's labeling them with the energy cost. How many microjoules do each of those transitions cost? And so what we need to know is how often do those transitions happen? And some of those are discernible by the compiler, and some of them are selectable by the programmer. So for example, the sampling rate of a sensor is going to drive how often the particular event that delivers new sensor data happens. And so a programmer might decide to change that sampling rate in order to use more or less power. And in the lower left here, I know it's too small to see, is a set of equations representing the model of the memory use and energy use of this application, and a little bar that's showing the battery life of the Amulet. So let's see what this looks like in a live view. So we have this online. It's a publicly accessible website that is able to give you a feeling for what this tool looks like. It's kind of nice because you can rearrange your state machine to make the diagram a little prettier. This is, not our software that makes that possible, but it makes it a very readable approach. And then I can pick different applications here. If I want to look at different apps, I can just pick a different app here. So the temperature sensor is a very simple state machine. Now I've messed up this heart rate app. Okay, and then down here are sliders, so I can adjust the amount of the frequency of this event on the transition on the bottom, and I can adjust every other transition here at different frequencies. And you can see in the very bottom of the screen here, there's a blue bar that's adjusting. It's telling you what the lifetime of the amulet will be with this mix of apps and that parameter setting, that event frequency. Some of these events are things that the programmer can control, like the sampling rate of a sensor, and some are their best guess as to how often the user will press a button or how often the light level might change from one reading before, and so forth. And it also shows the memory usage, and you can sort of get a sense of how your app will impact the overall amulet. So we found that to be a pretty useful tool for programmers. So let's evaluate the amulet. So we built 9 different applications to get a sense of how they run on the amulet. There are 6 screenshots here, just because there was only room for 6. And then the bar chart on the right shows the lifetime on the y-axis. The power on the y-axis. The power on the y-axis and the applications on the x-axis. And there's a label on each bar that shows you the lifetime of the amulet if it were running only that app. And the ones that consume more power have a higher bar, have a shorter lifetime, not surprisingly. Interestingly, the HR logging app, the heart rate logging app, used up the battery the quickest. It only lasted 2 weeks. And that's because it was writing the heart rate to the micro SD card every time it collected a new heart rate. And that SD card turns out to be one of the most power-hungry pieces of the amulet. And so if you write an app that uses the SD card a lot, you'll find that it's going to impact the lifetime significantly. But you can also see that there are several others that allowed the app to run for the better part of a year without recharging the amulet. So this is good. This means that we're likely to achieve our goal here of a very long-lived wearable device. The other thing we wanted to evaluate was how well that nice graphical tool and the models underneath it actually predict the lifetime. Most app developers don't want to wait 8 months to see if their app will last 8 months. They want to know if that prediction of 8-month lifetime is actually going to be true. And so we want to compare the predictions with those actual measurements. So we took those 9 applications, and you can see in this chart 4 columns, the observed power consumption in microwatts, the predicted power consumption in microwatts, and the error, that is the difference, and the percent error. And you can see that we were pretty darn close. We got within 90 to 98% accuracy of the prediction relative to the actual power consumption. And it looks like, in most cases, we were overestimating the power, meaning underestimating the lifetime, which is probably the best way to be if you're going to be off. And I'm sure we can improve this. There are some things that we didn't model as carefully as we could have. For example, SD card writes. The energy cost actually depends on how many bytes you write. And we just charged a constant cost, and so we could model that a little more accurately. We also did 2 user studies. The first we wanted to do was for developers. Remember I said we wanted it to be usable both for the developers and for the person wearing the amulet. And so we wanted to see if these developers would find this ArtView to be usable and helpful. And so we got 10 programmers, students, who had some experience writing embedded systems code, but not a lot, and no experience with the amulet. And we gave them a brief sort of tutorial, here's how you write code for the amulet, and then asked them to do a task for 30 minutes to write an application with and without this ArtView. And we found that, I'm just glossing over this very quickly, but they found this ArtView was very helpful. It kept energy sort of front of mind as an important characteristic, and they were able to much more easily make design decisions about which approach to take to minimize energy use. The second study was to put it on volunteers, put the amulet on volunteers and have them wear it for a week and see what they thought and see how well we could collect data. It's not an effort to actually do some sort of a health study. Although we did this with our healthcare partners, this data is not like proving that the amulet can help reduce stress or something. No, the goal is just to find out how well the amulet works, how efficient it is, what works well for people and what didn't. So we had them wear a Bluetooth heart rate sensor. It's a Mio, which is actually a wristband, and an amulet. And it collected the heart rate constantly, and it presented an EMA, an ecological momentary assessment, a survey question a couple of times a day, sort of asking them, how stressed do you feel, that sort of thing. And so we had 6 people for a week, very small study, but just to get a sense of how well the amulet worked. And the main goal was for us to get feedback about what doesn't work in the amulet and improve it. This was done actually last spring, and we've made a lot of improvements as a result. General story here is that it worked reasonably well. One lesson I learned on the first day when a subject called to say, it's leaking blue liquid all over my wrist. And I said to the guys, what the heck is going on? We don't have a liquid in our amulet. Why is it leaking blue liquid? Well, it turns out that the grad student needed to quickly label each of the amulets that we had with the 1, 2, 3, 4, 5, so we could distinguish them. He grabbed a dry erase marker and he wrote it on there in blue marker. And of course, the subject went for a run, got all sweaty, and it just leached all this blue ink off of the amulet onto the subject. Whew, boy, it's a good thing it was just ink. But that was a lesson learned. Don't use dry erase markers to label your hardware. So we gave this talk at Census. And by the way, if you're interested in the details, the Census paper has a lot more. Just a couple of weeks ago, and here's some of the questions that came up. So why did we build a custom operating system? There are other embedded operating systems out there. And the main reason is that they really didn't have the combination of features that we felt were really critical. One was this application isolation. Ours is designed for multiple applications by different developers, and we need to isolate those apps. And resource profiling. We wanted compile time ability to statically analyze the tool and understand its resource consumption. And the second one it reflects a limitation. How does the Amulet operating system decide what sensors schedules to honor? So if you have multiple apps, let's say this one wants a 20 hertz sampling rate on the accelerometer, and this one wants a 100 hertz sampling rate on the accelerometer. Right now we say tough. Everybody gets 100 hertz, whether they want it or not. It's decided globally. To actually adjudicate those multiple applications' different needs would require another layer of resource management and allocation algorithm that we haven't yet done. Another relates to the model. So how do you, when you have a sensor or something like that that is used by multiple applications, how do you allocate that energy consumption to an app? And the answer is we don't. We actually allocate it globally. Our main goal is to estimate the battery lifetime of the Amulet as a whole. And so if one or more apps are using the accelerometer, then the accelerometer is on, and that energy is consumed as part of the model. And each application's use of the accelerometer data is modeled as part of its code. Another one was, hey, where can I get one? So we don't make them or sell them, but they are available. You can download the specs and the hardware CAD designs and so forth and make your own. We'd be thrilled to have you to help. You know, we'd like to see people use this. So to summarize Amulet, it's a secure multi-application platform with a compiler-enforced app isolation. This is on a microcontroller that really has no hardware support for that kind of thing. It's open, hardware and software. It's got great battery life. It has an energy modeling tool that seems to be pretty accurate. And it's fairly usable, I think. It's an ongoing project. We're improving the Amulet all the time. Even the pictures that I had in this talk are slightly out of date. And I'll show you some new ones here in a moment. Oh, yeah, here they are. So this is what the Amulet, what we call the Kite version B, looks like. We keep improving the case design and so forth. And you can probably see here, I should have zoomed in, but so this is the capacitive touch slider here on the left. There's 5 little pads there. Each are a capacitive pad. And as you move your finger, you touch different cap touch pads, and you can get the effect of a slider. This up here is the light sensor. This is the programmer's port. So in order to install firmware, now you have to do it over a wire. We hope to do that over the air. There are a couple of holes here that are for the temperature sensor, one of the other light sensors, LEDs. There's 2 buttons on the left, and maybe a little more visible here. It's really interesting. This 3D printer has a soft plastic, kind of almost like a rubber. So they're actually squishy, pushable buttons. And you can see different apps running on the display here. You can see that we can get different font sizes, even a little bit of graphics out of it. It's kind of nice. It's a little harder to see here, but there's the micro SD card is spring-loaded out the side there. One thing that our research friends and users tell us they want is water resistance. And I don't think we're going to get that with this relatively open case, but we're working on it. Lots of things to do. We want to write more applications. We now have a working platform and really want to put emphasis on doing stuff with it. We also want to complete the firmware tool chain to make it to support over-the-air firmware updates. Also that data flow chain from the Amulet to the smartphone to the cloud to the end user. And I have an undergraduate who's focused on using attribute-based encryption to support multiple different destinations of the same encrypted data flow. We want to loosen some of the restrictions on C to make it a little more flexible, but also maintain our security. We want to do work on the network. It's a BLE, so we're limited by what BLE can do, but we want to expand to include other kinds of sensors. We're building our own custom GSR and heart rate variability sensors that hopefully will integrate soon. And some of the more ambitious students are interested in harvested energy, so you're not having to recharge ever, if possible. It's a large team. This is the set of people involved as of October. And there are several students before that who have graduated already. There's a full list of names, mostly people, students at Dartmouth and in Clemson, some of whom now are graduated in other places. This was supported by NSF and by the SHARPS program before that, Health and Human Services. It's our work, not theirs. And I just wanted to mention 2 other things briefly. One is that we also have a large related project called THAW, Trustworthy Health and Wellness. So if you're really interested in the cross between mHealth, security, and privacy, check out thaw.org as well as amuletproject.org, because this is a project that involves Dartmouth, Michigan, Illinois, Hopkins, and Vanderbilt faculty and students working on a wide range of projects around that space. And then I also wanted to mention Dartmouth is hiring. So if you're a grad student and you're looking for faculty positions, this year we're hiring junior machine learning and senior level cybersecurity folks. Next year I'm sure we'll be hiring again. So if you're not quite ready, don't forget to check us out. We're also looking for grad students. So if you're an undergrad or if you have undergrad friends, we are looking for really strong grad students who might want to come and do this kind of work. The applications are due pretty soon. Just to give you a context, Dartmouth Computer Science is a great department, very strong, but certainly smaller than, say, at a place like UW. We have 30 faculty members, about 21 tenure track, and the others research faculty and adjunct faculty, and about 100 graduate students at any given time. It's got some really strong faculty in mobile systems, in computational biology, in robotics, in machine learning, in digital arts, which includes vision and graphics and so forth. So a lot of cool stuff going on. And one of the things I really like about it is the interdisciplinary connections. So we see, of course, CS is the center of the universe, but we work with people in the medical school, the engineering school, the hospital, and in the social sciences extensively. So it's a nice place to be. And with that, I'm happy to take questions. Thank you. Richard.
You didn't say anything about the cost of the device, so just wondering about bill of materials.
Yeah, so it's $55 at the last time we estimated it to fabricate the device. I mean, in the quantities we do, which is 5 and 10, something like that. So it's not, you know, these are cheap things, an MSP 430 and so forth. Yeah.
Correct.
So one of my dreams has been to build a phone using the e-ink display that you're using. Can you tell me sourcing that, how hard it is to program, how hard it is to use in general? I'm very curious. It's the first use I've seen of it. outside of those Amazon things that know comprising.
The question was about the display. It's not strictly speaking e-ink, which is a particular brand and a particular technology. It's a related technology. As I understand it, e-ink retains its image with no power. Ours does require a tiny bit of power. It was easy to source. As far as I know, it's not been a challenge to get. We buy them and make new amulets all the time. I don't think it was particularly hard to program. You notice that you can either treat it as a set of lines of text with a certain font, or if you want to be really simple, or you can address every pixel and draw little graphics like hearts or bar graphs, as you saw. So I can connect you with the students who would know a lot more about that.
Other questions?
Yeah.
You mentioned that apps have sort of access control on which sensors that they talk to. Is that exposed to the user at all? If someone gets an amulet, say, from their healthcare provider, is there a way that they can know what about them is being tracked?
That's a great question. You were asking about the access control that we impose on apps' access to sensors and whether the user, meaning the wearer, the person wearing the amulet, has an awareness or control over that. And we have not addressed that broader question. Right now, it's a very, frankly, sort of clunky solution. There's a little configuration file that just says which apps have access to which API functions, which can effectively limit their access to the sensors. But there's, in my mind, still a broader and important question about how you would do that kind of, what would be the HCI, the UI, to the user? Would that be done in, for example, the app selection process when I'm clicking, okay, I want to choose these apps? One of the models that I have in mind is that a doctor would recommend apps, or some trusted person, somebody you trust would recommend, I recommend this app for you. But then you as the user would have to say, yes, I want that app on my amulet. And presumably at that point, there would be some information about what that app does. And that would include what information it's collecting. But we just really haven't had time to look at that broader question.
Any more questions? Curtis.
I had so many questions. So this is, obviously, I'm super interested in the work. One of the weird dichotomies I've seen in this kind of stuff is there's like the Ubicom people and then there's the design people. Kimiko at Berkeley High School, for instance, built these like really interesting full-on like dresses that are programmable, and they're usually for design aesthetics. Like you have interesting patterns showing up and lights and things like this changing versus sensors. But it seems like there's an immediate spot for taking the kind of stuff you're doing and expanding it into the design world, so it's not a wristband, it's everything. I just kind of wanted your perspective on that kind of growth from this work.
Yeah, so you were asking about whether this could be expanded beyond the wrist and into a broader range of design possibilities. And we've always envisioned from the start that the amulet was a device that served certain functions, but where it was located was sort of open. We started with the wrist because we thought, we could build something small enough to fit on a wrist, but to make it smaller to be, a ring or a pendant or something like that would be a little bit harder. I think there are different design challenges, different UI challenges, depending on where you put it. Obviously, your ability to interact with a pendant is very different than your ability to interact with a wristband. I am interested in expanding Amulet in terms of its into the clothing space. I have a student starting next month, actually, who wants to do smart clothing. And so I was imagining more of a sensor or an output device that would talk to the amulet, but that would be a shirt or pants or a belt or whatever, some sort of article of clothing. So I agree, I think, with what you're saying, which is that there's a lot more space there. We do have a couple of HCI experts on the team who are really interested in, what kind of buttons, and are they on the left or are they on the right, and how does the UI work, and all those issues. But the actual physical design, we don't have the expertise on our team for that. And it shows.
So I might ask one question then. So, I'm very interested in your ability to kind of predict the power usage of different applications, and I'm wondering to what extent you've thought about or think you might think about the degree that a security person could leverage that capability to figure out the most efficient type of power-based denial of service attack against a system, or the weaknesses of the system for information leakage, meaning if an application has the ability to monitor power, they can sometimes learn information about what other applications are doing. Kind of flipping it on its head and use it as a security analysis tool.
Yeah, that's very interesting. We haven't completely mapped out how the whole ecosystem would work. But as you might have gathered from the big picture diagram, all the apps go into the cloud, and then the cloud produces the firmware, which means that the cloud has to have all the app source code. And so there's an issue there, perhaps an IP issue. App developers may not want to give their source code to the cloud. The end user doesn't get the source code, but it does get the resource profile. An app developer would. So your point, if I was a malicious app developer and I had downloaded these profiles for all these other apps, I could actually look at the state machines and the way those other apps behave. So there's a huge opening there. And then we do allow the apps to sense the battery level for probably obvious reasons, and so that could allow them to infer what other apps are doing. Most of our focus has been on memory isolation and not so much on side channels or other forms of interference between apps. So there's a lot to be done at this point. But hey, get your own Amulet and go for it.
Sounds good. More questions? Yeah, maybe one more.
So I was wondering why you decided to go kind of battery or power first when you were thinking about how you might help app designers or developers. Like, what's the core use case that you see developers going for where battery is really the most important thing, rather when we live in a world where someone might be able to plug in their device overnight or something like that?
So that's a great question. Why does our tool focus on battery life first? And it's probably because our philosophy of the Amulet has been to allow for continuous long-term monitoring of a user. I know that as a user of myself, of Fitbits and wearables of that type, that I often either forget to recharge it and it dies, or I put it on the charger and then forget to wear it the next day. And so if my goal, or if my doctor's goal, or if the researcher's goal is to collect continuous long-term data about the person, then all of those are problems. And so we were hoping that we would have a solution that would last at least a week so that you could avoid those problems. And so that means that you need both the system design, hardware, software, and the applications to be designed to last a long time. So that's I guess, an expression of our kind of philosophy, that power is really important. It's one design point, right? One could imagine others where power is less critical. But my own experience shows that recharging is a problem.
Okay, well, let's thank David.
Thank you.